Hi. So in this video, our intention is to discuss about something called Stokes law. By the name suggests, Stokes law. This law is given by Sir George G. Stokes. It's not a fundamental law, but it's an empirical law. I hope you will find the difference between these. No? What exactly this law tells us? It explains, how when a body is moving through fluid, the viscous drag or the viscous force which was experienced by the body. So this explains the viscous drag on a body when it is going to explain when this body is flowing through the fluid. Okay, so this is about specialty about now we are writing an expression for this. Okay, so this is going to explain about that. Now before moving ahead, I would like to share you one picture. I hope it's relevant to this discussion. I believe that. Let me resize it a bit. Okay. So, when a body is flowing through a fluid, which is having some kind of viscosity, we know that the fluid flows, our fluid has layers, right? Say that this is a metallic ball and which is spherical in nature. When it is flowing through it, and the layer which is in contact with the body, say this or this, it moves with the same velocity with which the ball is moving. And if you go extend like this, if you go far away, the layers which are away from the object, right, they remains at rest only. So which means what I'm trying to say is the layers which are in contact are moving with the velocity with which the object is moving, and the layers which are away from the object are moving or there remains at rest, which means to say that there is some kind of a motion. What kind of motion? It's a relative motion between the different layers of the fluid. That's what I'm trying to say. Because of this body experience some kind of an opposition from the fluid which try to prevent the motion or which try to retard the motion of the spherical ball. Okay, so this retarding force, whatever we have, as the velocity of the body increases, this retarding force also increases. And I have shown here Fd as retarding force or drag force. Okay, Fg as gravitational force, or because of the weight of the body, I can say. I would like to share a few observations which was made by Sir George Stokes. His observations are like this. So when a spherical object is dropped in a fluid, say that the viscous force, whatever he observed, the viscous force F is proportional to few of the things. Is proportional to what are those? One is the velocity of the object, which is flowing or which is going through the fluid. Okay. Not only this, the radius of the object or the radius of the sphere which you have taken, the radius of the sphere, also the viscosity. Here, Stokes has observed for only spherical objects. Okay. Viscosity of the fluid. So if you write in the form of expression, we'll write F is proportional to velocity V, radius of the sphere, let us take R, viscosity or coefficient of viscosity, eta. To remove this proportionality, we use a constant called K, okay, which is our proportionality constant. So V R eta F. So this whatever we have written, this is an expression for Stokes law, but yeah, the value of K is found to be from the experiments. Value of K is 6 pi. I hope it's right. Yeah, 6 pi. So you can write Stokes law, which gives you an idea about viscous force experienced by the metallic sphere or the any kind of a spherical object. 6 pi V R eta. You can even rearrange this expression. where V is the velocity of the metal, V is the velocity of the spherical object, R is the radius, theta is the coefficient of viscosity or viscosity of the fluid, you can say. As an exercise, okay, everyone try to uh, check the correctness of this equation, okay, using dimensional analysis. What you are supposed to do? Correctness, whether the given equation is dimensionally correct or not. Correctness of the adjacent equation. Check it using dimensional analysis. Using dimensional analysis. This is your homework. Please do this. Stop here.